Today we'll derive an expression for the electric potential due to an electric dipole. An electric dipole consists of two equal but opposite charges separated by a small distance. Let's first define the dipole moment. The dipole moment, P, is equal to Q times D, where Q is the magnitude of either charge, and D is the vector pointing from the negative to the positive charge. Now, let's consider a point P at position, where we want to calculate the potential. The potential at P will be the sum of the potentials due to each charge. For a point charge, we know that the potential is given by kq over r, where k is Coulomb's constant. The total potential at P is the sum of potentials from both charges. It's kq over r plus for the positive charge, minus kq over r minus for the negative charge. For points far away from the dipole, where r is much larger than d, we can approximate the distances r plus and r minus using the binomial expansion. Substituting these approximations and using the binomial expansion for small x, we arrive at our final result. The potential due to a dipole is k times p dot r over r cubed. This expression shows us two important things. First, the potential falls off as 1 over r cubed, much faster than the 1 over r dependence of a point charge. Second, the potential depends on the angle between the dipole moment and the position vector through the dot product. Welcome. Today we'll derive the expression for electric potential due to a point charge. Let's start by understanding what we're trying to find. The potential V at a point due to a point charge Q. First, recall that the electric field due to a point charge Q at a distance R is given by Coulomb's law, E equals kq over r squared in the radial direction. Here, k is Coulomb's constant, equal to 1 over 4 pi epsilon naught. To find the potential, we need to calculate the work done per unit charge in bringing a test charge from infinity to r point P. The potential difference between 2 points is given by the negative line integral of the electric field. Let's visualize this process. We're bringing a test charge from infinity along any path to r point P at distance r. Due to the radial nature of the electric field, we can choose a radial path to simplify our calculation. For our radial path, we can write the potential at point P as the integral from infinity to r of negative E dot doctor. Substituting our expression for E, we get negative kq over r squared dr. Now, let's solve this integral. The integral of 1 over r squared is negative 1 over r. Evaluating from infinity to r, we get k q times the quantity 1 over r minus 1 over infinity. Since 1 over infinity equals 0, our final expression for the potential is kq over r. This is our final expression for the electric potential due to a point charge. Notice that the potential varies as 1 over r, while the electric field varies as 1 over r squared. This means that the potential decreases more slowly with distance than the electric field. In conclusion, we've derived that the electric potential at a distance r from a point charge q is equal to kq over r. This fundamental result is crucial for understanding electric potential energy and voltage in electromagnetic systems. Let's understand what capacitance is and derive the expression for the capacitance of a parallel plate capacitor. Capacitance is defined as the ability of a capacitor to store electric charge per unit voltage across its plates. Mathematically, capacitance C equals charge Q divided by voltage V. Let's consider a parallel plate capacitor. It consists of two parallel conducting plates separated by a distance d. Each plate has an area A, and the plates carry equal and opposite charges plus Q and minus Q. The space between the plates is filled with a dielectric material with permittivity epsilon. The electric field between the plates is uniform and can be calculated using the surface charge density sigma. The electric field E equals sigma divided by epsilon, where sigma is the charge Q divided by area A. The voltage across the plates is related to the electric field by V equals E times D. Substituting our expression for E, we get V equals QD divided by epsilon A. Now let's substitute this expression for voltage into our original capacitance equation. C equals Q over V, which equals Q divided by QD over epsilon A. The Q's cancel out, giving us our final expression. C equals epsilon A over D. This expression shows that the capacitance is directly proportional to the area of the plates and the permittivity of the dielectric, and inversely proportional to the separation between the plates. This means we can increase capacitance by using larger plates, using a dielectric with higher permittivity, or decreasing the separation between the plates. Derive the expression for the effective capacitance of two capacitors in series. We'll do this step by step using fundamental principles. First, let's draw our circuit. We have two capacitors C1 and C2 connected in series. When connected in series, the same charge Q must exist on both capacitors. Let's consider the voltage across each capacitor. The voltage V1 across C1 is Q over C1, and the voltage V2 across C2 is Q over C2. In a series circuit, the total voltage V is the sum of the individual voltages. So, V equals V1 plus V2. Substituting our expressions for V1 and V2, we get V equals Q over C1 plus Q over C2. Now, for the equivalent capacitor C equivalent, we know that V equals Q over C equivalent. Since both expressions equal V, we can equate them. Q over C equivalent equals Q over C1 plus Q over C2. Dividing both sides by Q, we get 1 over C equivalent equals 1 over C1 plus 1 over C2. This formula can be generalized for n capacitors in series, where we sum the reciprocals of all individual capacitances. Let's verify this with a numerical example. If C1 equals 6 microfarads and C2 equals 3 microfarads, then 1 over C equivalent equals 1 over 6 plus 1 over 3, which gives us 1 over C equivalent equals 5 over 6 microfarads. Therefore, C equivalent equals 2 microfarads. This makes intuitive sense because when capacitors are in series, the total capacitance is always less than the smallest individual capacitance in the circuit. Derive the expression for the effective capacitance of two capacitors connected in parallel. First, let's draw our circuit diagram. We have two capacitors C1 and C2 connected in parallel. In a parallel combination, the voltage V across each capacitor is the same. Let's consider the charge on each capacitor. The charge Q1 on the first capacitor is C1 times V, and the charge Q2 on the second capacitor is C2 times V. The total charge Q stored in the parallel combination is the sum of the charges on each capacitor. So Q equals Q1 plus Q2. Substituting our expressions for Q1 and Q2, we get Q equals C1V plus C2V. Now, we know that for any capacitor, the charge Q is equal to the capacitance times the voltage. So for our equivalent capacitor, Q equals C equivalent times V. Since both expressions for Q must be equal, we can write C equivalent times V equals C1V plus C2V, dividing both sides by V. Assuming V is not 0, we get our final result. The equivalent capacitance equals C1 plus C2. This result shows that for capacitors in parallel, the total capacitance is simply the sum of the individual capacitances. This can be generalized for n capacitors in parallel as the sum from I equals 1 to n of Ci. This makes intuitive sense because in a parallel combination, each capacitor provides additional area for charge storage, increasing the total capacitance of the system. Welcome. Today we'll solve a problem about electric potential. We have 2-point charges, a positive charge of 5 times 10 to the negative 8 coulombs, and a negative charge of negative 3 times 10 to the negative 8 coulombs, separated by 16 centimeters. We need to find the points where the electric potential is 0. Let's start by drawing our system. Here we have our positive charge Q1 equal to 5 times 10 to the negative 8 coulombs, and our negative charge Q2 equal to negative 3 times 10 to the negative 8 coulombs. They are separated by a distance of 16 centimeters. To find points of 0 potential, we need to use the electric potential formula. The electric potential V due to a point charge is equal to K times Q divided by R, where K is Coulomb's constant, Q is the charge, and R is the distance from the charge. Since we have two charges, we'll use the principle of superposition. The total potential at any point is the sum of the potentials due to each charge. For 0 potential, this sum must equal 0. Let's call the distance from the negative charge to our point x. Then the distance from the positive charge will be 16 centimeters minus x. Substituting these into our equation. After solving this equation, we find that x equals 6 centimeters from the negative charge. Let's mark this point on our diagram. There's also a second point of 0 potential. It's located at 24 centimeters from the negative charge, or 8 centimeters beyond the positive charge. Let's mark this point as well. At these 2 points, the positive potential from the positive charge exactly cancels out the negative potential from the negative charge, resulting in zero net potential. Notice that one point is between the charges, while the other is outside them. And that completes our solution. We found 2 points where the electric potential is zero, one at 6 centimeters and another at 24 centimeters from the negative charge. Let's solve a problem about work done in moving a charge through an electric field. We have a square with side length 0.2 meters and 3 charges placed at 3 of its corners. The question asks us to find the work done in moving a positive 2 nanocoulomb charge from corner D to the center of the square. To solve this, we'll use the formula that work done equals charge times the change in electric potential. First, let's find the distance from any corner to the center of the square. For a square with side length A, the distance from a corner to the center is divided by the square root of 2. With our side length of 0.2 meters, this gives us 0.1414 meters. Now, to find the electric potential at the center, we'll use Coulomb's formula for electric potential, V equals K times Q over R, where K is Coulomb's constant, approximately 9 times 10 to the 9th Newton meters squared per Coulomb squared. Let's calculate the potential at the center due to each charge. For the 2 nanocoulomb charge at A, we get 127.17 volts. For the 4 nanocoulomb charge at B, we get 254.34 volts. And for the 8 nanocoulomb charge at C, we get 508.68 volts. The total potential at the center is the sum of these 3 potentials, which gives us 890.19 volts. At point D, since there are no charges there, the potential is 0 volts. Finally, we can calculate the work done by multiplying the charge being moved 2 nanocoulombs by the change in potential, which is 890.19 volts. This gives us 1.78 times 10 to the minus 6 joules. And that's our answer. The work done to move the 2 nanocoulomb charge from corner D to the center of the square is 1.78 times 10 to the minus 6 joules. Let's solve a problem about energy stored in capacitors. We have an 800 picofarad capacitor charged by a 100-volt battery. We need to find the energy stored in the capacitor, and then what happens when we connect it to another identical capacitor. Let's start with the initial setup. Here's our capacitor connected to the battery. The energy stored in a capacitor is given by 1/2 times capacitance times voltage squared. Let's plug in our values. We have 800 picofarads, or 800 times 10 to the negative 12 farads, and 100 volts squared. Calculating this out, we get 4 times 10 to the negative 6 joules. Now for the second part. We disconnect the capacitor from the battery and connect it to another identical 800 picofarad capacitor. The capacitors are now in parallel. When we connect the capacitors, the charge is conserved, but it's now spread across both capacitors. The total capacitance doubles to 1,600 picofarads, but the voltage across each capacitor drops to 50 volts. Let's calculate the final energy using the same formula as before, but with our new values we get 2 times 10 to the negative 6 joules. Notice that the final energy is half of the initial energy. This is because some energy was lost in the process of connecting the capacitors. And that's our solution. The initial energy stored was 4 times 10 to the negative 6 joules, and the final energy of the system is 2 times 10 to the negative 6 joules. Let's solve a problem involving 2 capacitors in series connected to a battery. We have a 2 microfarad and an 8 microfarad capacitor connected in series across a 300-volt battery. We need to find the charge, potential difference, and energy stored in each capacitor. Let's start by drawing our circuit. Here are our 2 capacitors in series connected to a 300-volt battery. First, let's find the equivalent capacitance. For capacitors in series, we add the reciprocals. 1 over C equivalent equals 1 over C1 plus 1 over C2. Plugging in our values and solving, we get C equivalent equals 1.6 microfarads. Next, let's find the total charge. The charge Q equals the equivalent capacitance times the total voltage. That's 1.6 microfarads times 300 volts, which equals 4.8 times 10 to the negative 4th coulombs. In a series circuit, the charge is the same on each capacitor. So both capacitors have 4.8 times 10 to the negative 4th coulombs. Now let's find the potential difference across each capacitor. The voltage across a capacitor equals the charge divided by its capacitance. For the first capacitor, V1 equals Q over C1, which is 4.8 times 10 to the negative fourth divided by 2 microfarads, giving us 240 volts. For the second capacitor, we get 60 volts. Finally, let's calculate the energy stored in each capacitor. The energy U equals 1/2 times capacitance times voltage squared. For the first capacitor, that's 1/2 times 2 microfarads times 240 volts squared, giving us 5.76 times 10 to the negative second joules. And for the second capacitor, we get 1.44 times 10 to the negative second joules. Let's summarize our results. The charge on each capacitor is 4.8 times 10 to the negative fourth coulombs. The voltages are 240 volts and 60 volts. And the energies are 5.76 times 10 to the negative second joules and 1.44 times 10 to the negative second joules. Welcome. Today we'll solve a problem involving a parallel plate capacitor. We'll calculate its capacitance and the energy stored in it. Let's start by visualizing our parallel plate capacitor. We have two parallel plates separated by air. Each plate has an area of 6 times 10 to the negative 3 square meters, and they're separated by a distance of 3 millimeters. To find the capacitance, we'll use the formula. C equals epsilon naught times A over D, where epsilon naught is the permittivity of free space, which equals 8.854 times 10 to the negative 12 farads per meter. Let's substitute our values. We have epsilon naught times 6 times 10 to the negative 3 divided by 3 times 10 to the negative 3. Simplifying this gives us approximately 18 picofarads. Now we're told that the charge on each plate is 1.8 times 10 to the negative 9 coulombs. To find the energy stored, we'll use the formula. U equals 1/2 Q squared over C. Let's plug in our values. 1/2 times 1.8 times 10 to the negative 9 squared divided by 18 picofarads. This gives us 9 times 10 to the negative 8 joules. To summarize, we found that our parallel plate capacitor has a capacitance of 18 picofarads and stores 9 times 10 to the negative 8 joules of energy.